Hello everyone, we are Team Interplanetar, an undergraduate student robotics team from Bangladesh University of Engineering and Technology, presenting our latest rover, PROCHESTA version 5, and our UAV, Digonto, for the European Rover Challenge 2026. Team Interplanetar is a multidisciplinary student team of over 60 members, organized into 5 specialized sub-teams, each led by a dedicated sub-team lead.
I'm Abdullah, leading the software and autonomy sub-team. We have 6 members across 5 divisions: autonomous navigation, manual teleoperation, arm kinematics, drone, and graphical user interface.
I'm Zarif, leading the electrical sub-team with 7 members working across different board design, power distribution, and wireless system.
I'm Aswad, leading our mechanical design and manufacturing sub-team. 12 members work under 4 divisions: robotic arm, chassis and suspension, wheel and steering, and science.
I'm Rurana, leading the science analysis sub-team. We have 5 members across chemical analysis, geographical analysis, and model testing divisions.
I'm Onindo, leading the documentation and outreach sub-team of Team Interplanetar. We handle sponsorship, logistics, and team communications, supporting the technical team to make everything possible.
Team Interplanetar has been representing Bangladesh in international rover competitions since 2011. We entered the European Rover Challenge in 2022 with Renaissance V2, where we placed 8th in the on-site and 4th in the remote edition. And in ERC Remote 2025, we achieved a notable position. For us, ERC represents the highest standard in student rover competitions. It is where engineering meets real-life mission constraints, and we compete against the best teams in the world. Mars exploration is not an immediate reality for Bangladesh. We believe it is our responsibility to build that foundation, developing talent, pushing technical boundaries, and inspiring the next generation of engineers in a country where space robotics is still a growing field. That ambition and that responsibility is why we keep coming back to ERC.
PROCHESTA version 5 features a lightweight 4-wheeled rocker bogie suspension with a bar differential. The chassis and suspension are fabricated from TIG-welded stainless steel square tubes. For propulsion, we use hoverboard PLDC hub motors, driven by 2 O-drive boards. Our tires are custom 3D printed in TPU for improved grip and shock absorption on uneven terrain. Each wheel has been tested in simulation as well as real-life testing for secure performance.
For safety, an external hardware kill switch instantly cuts power to wheels, arm, and drill. A remote software kill switch at the ground station can also selectively disable individual power rails for better fault isolation.
Our centralized power distribution board provides regulated voltage range. From a 40-volt industrial 5S3P battery pack built with lithium-ion cells, complete with internal BMS protection. Rails are switched via MOSFETs for better thermal management, and an Arduino Nano provides live telemetry on an onboard OLED display. An addressable RGB LED strip serves as our activity indicator: green for manual mode, yellow for autonomous mode, and red when disarmed.
Our communication system uses a dual-link setup for the rover. The Rocker M2 operates on a 2.4 GHz band and serves as our primary high-bandwidth channel for ROS2 telemetry, video, and data transfer, using a sector antenna at the base station and an omnidirectional antenna on the rover. For the drone, we use a dedicated telemetry radio on 433 MHz for flight controller data and command uplink between the drone and the ground station. A separate FPV system provides real-time video feedback from the drone during flight operations. Navigation is achieved through sensor fusion of RTK GPS and visual odometry by Z2i depth camera. Our nav2 stack identifies steering hazards for dynamic path planning, ensuring fully autonomous traversal. The RTK GPS helps with GNSS-based navigation with our custom-built graphical user interface and traversal algorithm. The rover can also achieve Oroco marker-based navigation with a pre-built search pattern.
Digonto is a custom-built quadcopter drone based on F450 ABS frame.
The drone is powered by 4 BLDC motors, producing a total thrust of 3.7 kilograms and regulated by 30 ampere AC. The flight controller is a Pixel, paired with a Raspberry Pi 4B as the competent computer. For vision, Raspberry Pi 4V camera V3 handles the aeromarker detection, while an optical flow sensor and LiDAR rangefinder supports stable indoor position, where GPS is unreliable. The total flight weight of the drone is approximately 1.08 kg. Our drone software uses a dual environment architecture. Python with OpenCV handles the computer vision pipeline, detecting markers and computing spatial coordinates. These are fed into MATLAB-based navigation algorithm that generates autonomous flight trajectories and sends mapping commands to the pixel. For autonomous operation, the drone detects markers, navigates to each in sequence, captures an image on arrival, and lands upon task completion.
The rover arm has 5 degrees of freedom and is manufactured from TIG-welded stainless steel with an aluminum and 3D printed wrist assembly to minimize weight. Each joint includes a magnetic encoder for precise position feedback, and we run an inverse kinematic system for intuitive operator control. The end effector features 3D printed claws with integrated laser guides for precision. A dedicated servo-controlled poker mechanism allows keyboard interaction. With the aid of an onboard camera, the end effector can push buttons, flip switches, plug in USB connectors, and type on keyboards. With 360-degree continuous rolling, we can turn knobs and drive screws. The arm can pick up objects from the ground, pull ropes, open and close latches and drawers, and retrieve probes.
Our SANS module is designed to meet the full ERC sampling challenge, collecting deep soil cores, surface regolith, and liquid samples. For deep soil collection, we use an auger drilling mechanism capable of extracting soil from depths of up to 30 centimeters. The drill is mounted on a platform deployed via a lead screw mechanism, which converts rotary motion into precise linear descent. Aluminium C-plates and pole supports provide a rigid and lightweight structural frame. As the auger rotates, the spiral mechanism brings soil upwards, where it is deposited into a sealed storage container. Once the desired amount is collected, the container lid closes automatically to prevent contamination and spillage. For regolith and surface soil collection, the rover arm's gripper is used to grab and transfer samples directly into dedicated containers, keeping each sample type isolated. All sample containers are mounted on load cells that provide real-time mass measurements during collection. For chemical analysis, we process the soil samples directly in the lab. The soil is mixed with distilled water and the solution is transferred into test tubes, where specific reagents are added to observe visible color change. Laboratory tests additionally cover organic material detection, iron from phyllosilicates, pH, temperature, and NPK sensor readings for habitability analysis.
We are deeply grateful to our sponsors and partners for their continued support. Thank you for watching. We look forward to seeing you in ERC 2026.